right here, section 4, your credit utilization is simply too high.
But the projection clearly shows future growth.
The decision is final.
Welcome to The Explainer. Have you ever wondered how your phone knows it's you? Or how a car can drive itself? Well, today, we're cracking open the so-called black box behind all of it. We're talking about deep learning. You know, every major leap in technology really boils down to one thing: making our lives easier. Just look at how we communicate. We went from waiting days for a letter to having video calls in our pocket. It's always about removing human effort. And that exact same drive for convenience is what's fueling the next big leap for computers. We're shifting away from the old, clunky ways of teaching them and moving towards something that's way smarter. Okay, so let's get into it. The old approach, traditional machine learning, was pretty cool, but it had this one massive bottleneck. A person, a human engineer, had to sit there and write out every single rule by hand. And that right there is the crucial difference. It's a fundamental shift in who does the heavy lifting. In the old world, humans had to code all the rules. With deep learning, we just give the machine a goal, and it figures out the rules all by itself. I mean, just imagine trying to write down all the rules to define an apple. You'd say it's red, it's round, but what about a green one, or one with a leaf, or a brown spot? Suddenly, your rules don't work. The manual approach was just too rigid, too brittle. It just couldn't handle the messy, unpredictable real world. So, to solve this problem, researchers looked for inspiration from the best learning machine we know of, the human brain. And what they came up with was a new architecture called a neural network. This right here, this is the engine that powers all of deep learning. At its core, it's just a system of interconnected digital neurons that are designed to work together to spot patterns in data, kind of like our own brains do. And the way it's built is actually pretty logical. You've got the input layer, where raw data comes in. Think of these as the eyes. Then that data flows through the hidden layers. This is where all the thinking, the real heavy lifting happens. And finally, you get an answer out of the output layer, something simple like, yep, that's a cat. But how does it know what to look for? Well, this is where the real magic is. It's a concept called weights. Think of a weight as a little importance knob on every connection. As the network learns, it starts to figure out which clues matter. So for identifying a cat, it might learn to crank the weight way up for things like pointy ears and whiskers, and turn the weight way down for something like color. So we've built this digital brain, but a brain isn't much good if it can't actually learn, right? Well, how it learns is surprisingly intuitive. It learns from its mistakes. It's basically just trial and error on a massive scale. The whole process is this simple, powerful loop. First, the network takes a guess. Then it checks its guess against the right answer to see how wrong it was. That's the error. And here's the key. It then sends that error signal backwards through the whole network, telling each connection how to adjust its weight just a tiny bit to make a better guess next time. It does this over and over, millions of times. Now, to manage all this, we use a few key terms. An epoch is like one full study session where the network sees all the training material once. Since that can be a ton of data, we break it down into a batch, like studying one chapter at a time. And the learning rate? That's basically deciding how drastically to change your thinking after you get something wrong. Is it a huge adjustment or just a little nudge in the right direction? Okay, enough with the abstract theory. What does this all actually look like when we put it to work? Let's take something we do every second without thinking about it: seeing. And this right here perfectly captures the challenge. When you and I see a cat, a computer sees a giant grid of numbers. That's it. Each number just represents the brightness of one tiny pixel. Its entire job is to learn how to find the hidden pattern of a cat inside that giant sea of numbers. So, for a specific job like seeing, we bring in a specialist. It's called a convolutional neural network, or CNN. What's so clever about a CNN is that instead of looking at the whole image at once, it first scans it in little patches, looking for basic features, like edges, corners, and textures. Then it starts piecing those simple features together to understand the bigger picture. But to get good at this, these models are incredibly hungry for data. We're talking massive amounts. In one famous project, a model was shown 60,000 different pictures of clothes just to learn how to tell the difference between 10 things, like a t-shirt or a boot. The more you feed it, the smarter it gets. So we have this insanely powerful technology. But, and this is a really big but, it comes with a fundamental trade-off that has huge implications for all of us. Here's the deal. On one hand, you get incredible, often superhuman performance. On the other hand, you get what we call the black box problem. Because the network taught itself, its internal logic can be so mind-bogglingly complex that even the engineers who built it can't tell you exactly why it made a specific choice. We get the right answer, but we don't always know how.
And the funny thing is, we've already accepted this trade-off in so many parts of our daily lives. That Face ID that unlocks your phone, the smarts inside Siri or Google Assistant, even cutting-edge systems that analyze medical scans. They're all powered by these amazingly accurate but kind of mysterious black boxes.
And that leaves us with a really important question to think about. For the convenience of unlocking our phones, yeah, we're okay with a black box. But what happens when that same black box is deciding who gets a home loan, or helping a doctor with a diagnosis, or steering a car? At what point do we need to know why a machine made its choice before we're willing to trust it with the things that really matter? That's the conversation we all need to be having.